we have just one thing that I want to go over before I release you for the practice questions. But I wanted to let you know that you will have the rest of today and then all of class tomorrow to work on / ask questions about these practice questions. Thursday, I'm planning to do part of a quiz. It'll just be the multiple choice part. We'll do the paper 2 next week. If you are, I see there's lots and lots of names on this paper, so I recognize that it is the season for y'all to be in and out. It is going to be up to you to make up anything that you missed because you're in an exam. I will find out hopefully tomorrow. Hopefully I'll know by tomorrow morning if I am proctoring Thursday and Friday, so you guys know we have a reduced schedule or a delayed opening on Thursday and Friday. I will let you know if I'm going to be around here in the classroom or if I'm going to be busy proctoring, so that if you wanted to come in and ask questions or just hang out here and work on stuff, you would be free to do so. So I'll hopefully be able to let you know that tomorrow. So that's our plan, and this is going to be up through page 16 in the HL study guide. So we're going to do the Arrhenius equation and activation energy separately. So it'll be everything up to that, because it's kind of a whole different ball of wax. I mean, it's not really a different ball of wax, but it's different enough that I want to put it on a separate mini unit of its own. Okay. Again, if you didn't get a chance today, please, or if you couldn't remember which exams you're taking, then you can at any point in time can update what's on the clipboard up there. And again, if there's anything that I did not put on there, but maybe you're taking it somewhere else, or maybe it's a studio art thing that I didn't realize was going to be a call out thing, just write it in. Okay, so the last thing I wanted to do was go back to talking about calculating K, the rate constant K, and specifically talk about the units. So we did this a little bit a few days ago with one of the examples previously, but I didn't actually get to that part within the study guide. What they actually do here on page 15 is they go over something that we did together as sort of an extra bit. So this is from page 8. We went through calculating the order of reaction with respect to the different reactants. We found that the rate for this particular reaction rate expression was K times the concentration of NO to the second power, concentration of O2 to the first power. So we're first order with respect to oxygen, second order with respect to the NO. And then we already did this where we picked one of these rows and use the data in order to calculate K. So we have the rate, and we have the concentrations of the two reactants, and we just plug them into our rate expression, and we calculate K. What was tricky when we did this was that the units were a little bit tricky, and the units are going to depend on the order of the reaction, because that's going to determine how many moles per decimeter cubed you have in the numerator and the denominator of when you solve for K. All right, so just to remind you, this was these were the slides from back then. We did the numerical equation, so we took our rate, we plugged in our concentrations, and then we divided everything by the concentrations. We divided both sides by everything in order to get K by itself. And when we did that, we got this number, which was 25. And then, which again is also on page 15 of your study guide. And then we also went and talked about how you would do this in terms of the units. So we have units for the rate is going to be moles per decimeter cubed, usually per second. If it's for some reason not per second, that's probably something to pay attention to. That's come up once or twice, where it's been per minute instead of per second. Hi. Oh, thank you. And then each of the concentrations is also moles per decimeter cubed, right? That's our standard solution concentration, or concentration of a gas in this case. So moles per liter, moles per decimeter cubed. And we have to make sure that we square anything that is second order, and then basically multiply them all together. So what we basically end up with here, when we move this term over to the other side, to the denominator, to solve for K, is we have our moles per decimeter cubed per second here, and then we're dividing by moles per decimeter cubed in this case, okay? Because we have an overall third order reaction. Second order with respect to one, first order with respect to the other, overall third order. And when we cube something, we multiply the exponents. So here we have moles cubed, decimeters to the negative ninth. And when we divide exponents, we subtract them. So we end up with moles being to the first minus the third, right, which ends up being moles to the negative 2. Our decimeters ends up being negative third minus negative 9, which ends up being positive 6. And then the seconds isn't canceled out on the bottom, so we just leave the seconds to the negative 1 there. Okay. So you can always derive this from the units that go into the equation, that go into solving for K. Okay, you can always derive this. However, you can also, if this is more up your alley, you can also just memorize what the units are going to be for different types of reactions. Okay, because it's always going to be the same, because the only thing that's changing is how many moles per decimeter cubed we have in the denominator, right? Or how many we have on the K side of the equation. And if it's a zero order, then we don't have anything on that. If it's overall a zero order reaction, then it's just the rate, the units of K is just the units of the rate, right? Because the K is going to be equal to the rate. If it is first order, then we're going to have 1 moles per decimeter cubed in the denominator, canceling the 1 moles per decimeter cubed from the rate units. So all that's going to be left over is the seconds to the negative 1. Second order, we're going to have 2 moles per decimeter cubed in the denominator. So we're going to cancel one of those, and then we're going to end up with the opposite signs, because it's in the denominator of our moles and our decimeters cubed. And the seconds is still going to stay there. Seconds to the negative 1 is going to be there in all of them. And then here's our third order, like we just did, with the moles to the negative 2, decimeters to the 6th. So if you're the kind of person who likes to see it this way and likes to think of it as, okay, I know it's third order, so this is going to have to be the units, and I have that more or less memorized, or at my fingertips, great. Then know that this is always going to be the units for these different or overall orders of reaction. Okay, and it's important that we pay attention to the fact that it's the overall order, not just per any given reactant. But again, you can always derive it just by using the units in your equation where you're solving for K. Okay. I believe that is all I have. Yep. Somebody asked in the practice questions, in the first question, if the rates of the second 2 experiments were 10 to the negative 6th or 10 to the negative 8th. That is a 6 there, so 1.0 times 10 to the negative 6th, then 1.9 times 10 to the negative 6th, in case that was hard to see. If there's anything else you're not sure about, let me know. I did throw in one of the answer choices here is just something that we haven't gotten to yet, so I'm just telling you that number 3 is correct. But you will learn that when we get to organic. Okay. Any questions at this time? All right.